Today's topic is data transmission probability of error. Today we are going to talk about how the data is transmitted in a digital communication so that the receiver the probability of error is getting. That is the one of the main important point. Today we will see where see here the signal if at all is transmitted the symbol, either bits or symbols, MI is represented, and that is being represented with a signal vector SI of T. And so that this is being transmitted over a channel, and in the channel, A2 white Gaussian noise is being added, and the signal is received at the receiver, signal plus noise. So this is what X of T where S of T, Si of T, signal plus W of T is the noise added, the X of T is the received signal. This signal, the symbol or bit digital data is represented during the transmission bit 0 to TB. So if at all there are number of signals I equal to 1 and 2, S1 and S2, etc. So the signal vector is represented X is Si plus W. So in this space diagram, if at all you see that signal vector is represented in this vector and noise vector is added here. And the resultant vector, the received vector is located here away from the message. So that is what in the noise region, in this noise region, how far the received vector is lying so that the amount of noise is being added to the signal vector. So in this space diagram, that signal vector is represented in an n-dimensional space diagram. So this phi 1, phi 2, phi 3, etc. is the orthonormal basis functions. So now, if we see this space diagram, as the number of symbols here, message 1 and 2 and 3 and 4 is given as an example. And the bisection of these two signal vectors, if at all you combine these two signals, the perpendicular direction, the bisection of these two signals is the boundary region. Similarly, for all the signals is having some boundary. So the region, the each signal of having this region, boundary region Z1 and the region Z2, region Z3, region Z4 corresponding to the message S1, S2, S3, S4, etc. So as long as the received vector, this is the signal vector, and the received vector is lying within this boundary region of Z1, so that there would not be any error, because the decision making the message, the received message will be taken as the message point 1 as S1. So if the received vector is lying somewhere above the other region, other than Z1 region, when message point 1 is transmitted, so because of the noise vector, this received vector is lying somewhere in other region. So there is a possibility of getting error. So this is what we would like to measure or estimate the signal having some probability of error in the receiving, the decision making at the receiver. So we would like to see whenever the probability of error is calculated, whenever the SI is transmitted and there is a the signal which is closer to SK, S1 and S2, like S1 is transmitted, the signal is received at closer to S2, like that. So the probability of error which is measured if received vector X is closer to SK when SI is sent. So that is what probability of the error we would like to find. To measure that probability of error, we would like to integrate the probability density function of the Gaussian white Gaussian noise, which is being added here, and that is being integrated, or half the the Euclidean distance, this is the Euclidean distance dik, where between message 1 and message 2, half the Euclidean distance above of the Euclidean distance to the infinity region that is being under a probability of error. So that is what we would like to estimate the probability of error by integrating the boundary region of dik by 2 of the Euclidean distance towards infinity, that probability density function. Because the signal is being added with the white Gaussian noise, the probability density function of Gaussian distribution taken as this Gaussian distribution having mean and variance mu and sigma square, the probability density function of random variable x can be taken as 1 by root pi 2 pi sigma square e power minus x minus mu square by 2 sigma square, where mu is the mean, sigma square is the variance. So we integrate this probability density function over a of the Euclidean distance towards infinity. So then this is the probability of error we measure, we estimate. So if you simplify this function to express in complementary error function of like this, where complementary error function is a decreasing function exponentially integral u to infinity e power minus z square dz. This is complementary error function. So 2 by root pi sigma integral u to infinity exponential minus z square dz. This is what complementary error function of u. So this is the lower limit we take. So the Euclidean distance between S1 and S2 or Si and Sk, this is the norm between the distance we consider. So by solving this function, by integrating over to express in the complementary error function of exponential e power minus z square, so you express this is e power minus z square, you can take it as z square equal to x square by 2 sigma square, where mean is 0, taken as a random variable, mean is 0. So then z equal to x by 2 root 2 sigma square. You substitute here e power minus z square, then the integral becomes the lower limit dik by 2, where you lower limit is dik by 2 by root 2 sigma square. So that is nothing but dik by 2 root 2 sigma. Under root sigma square is sigma. This upper limit infinity becomes infinity. So by taking e power minus z square, this is what dz equal to dx into divided by root 2 sigma. Root 2 sigma square under root. Okay. So this is where dx equal to root 2 sigma square. So this 1 by 2 pi root sigma square, okay, e power minus z square dz. So that is what dx equal to dz 2 sigma square. So this is gets cancelled, and so that 1 by root pi e power minus z square dz. This lower limit is dik by 2 root 2 sigma towards infinity. This is what this function. Now we express as complementary error function, equating these, so we get a half complementary error function dik by 2 root 2 sigma as u. U is the lower limit. So this probability of error is expressed in complementary error function dik by 2 root 2 sigma. So if at all we consider dik is the Euclidean distance between any two signals. So this Euclidean distance dik as this is distance is more, then the probability of error is less, because the boundary having the region of getting in other region is less probable. So this is the energy we consider of any signal of S1 or S2. And this is what the energy, if more energy, the equivalent distance is more. So high equivalent distance, the equivalent distance is large, the probability of error is less probable. That is what the complementary error function of the complementary error function. This is what the complementary error function of u. So where e power minus z square dz. So this is where the decreasing function. So this is how we measure the probability of error in terms of equivalent distance and variance. Now, if you see the probability of error for the matched filter, if at all the probability of error is taken as the integrating the probability density function and lower limit dak by 2 root 2 sigma to infinity, where the matched filter, which is optimum filter, and considering white Gaussian noise, the variance is n naught by 2. So variance is n naught by 2. So if you substitute here 2 dak by 2 root 2 n naught by 2 under root. So this one gets cancelled, dak by 2 root n naught to infinity. So this is expressed 1 by root pi e power minus z square dz. So where the lower limit, it is expressed in complementary error function, half complementary error function of dak by root 2 root n naught. So the same thing where earlier the probability of error is dak by 2 root 2 sigma. So this is where dak by 2 root 2 sigma, where this sigma is n naught by 2. So this gets cancelled and dak by 2 root n. So the probability of error of any digital data transmission, either binary 1 and binary 0, while transmitting, if binary 1 is transmitted, received as a binary 0 in the decision making, while the received signal vector is lying in other region closer to binary 0. So that is what expressed in terms of equivalent distance. So if equivalent distance is more between two symbols or binary 1 or binary 0 digital data, the probability of error is less in that case. So that is how the probability of error is estimated. Thank you very much.